Hello students and welcome to a new lecture. This lecture is about the valence bond theory. When we have two atoms, like the two hydrogen atoms coming in the picture, the electron density between the two atoms keep changing till it reaches the maximum best overlap to provide the lowest energy possible for the system, which is where the system or the bond or the molecule, if you wish, is most stable, which is exactly what we want. Now here is an example. For a hydrogen molecule, you're going to have two hydrogen atoms. Each one of them brings the 1s orbital to overlap and give you the hydrogen molecule. For a hydrogen chloride molecule, the 1s orbital has the electron and one of the 3p orbitals has another electron. They overlap together and they give me the hydrogen chloride molecule. For a chlorine, then one electron from 3p and the other electron from 3p, they overlap together as the two 3p orbitals overlap, and that will give me the chlorine-chlorine single bond. So this valence bond theory simply said that the atom uses its atomic orbital to overlap with another atom atomic orbital to give the bond. So hydrogen 1s with hydrogen 1s, hydrogen 1s with a chlorine 3p, and so on. Now the problem with that model that it did fail to explain something about the ammonia molecule. So let's look at what was that. This is the electron configuration of nitrogen. 2 electrons in 1s, 2 electrons in 2s, and 3 electrons in 2p. Now, if you remember, there are 3 2p's. There is 2px, 2py, and 2pz. Now, hydrogens, each one of them has 1 electron in the 1s orbital. So, if I am making ammonia by pairing every 1s electron from hydrogen with one of the 2p electrons from nitrogen, then this is how I'm making those 3 covalent bonds between nitrogen and hydrogen. Remember, this is here ammonia. This is the Lewis structure of ammonia. I have 3 covalent bonds. And this model is trying to explain that this covalent bond is made of 1s with px. This here is made of 1s from another hydrogen with py. And this one here is made of 1s from another hydrogen with pz. That is how the bonds are being explained based on the valence bond theory. If that is the case, then the angle between these 3 bonds should be equivalent to the angles between px, py, and pz. And you know that these are on the 3 axes, x, y, and z, so the angle should have been 90 degrees. However, what we found that the predicted angle should have been 90 degrees, but the actual one was 107.3. That led us to not to believe that it's a simple overlap between atomic orbitals, because if it was, the angle should have been 90. That's XYZ is 90 degrees. But it's not, so then it's not really a simple usage of the atomic orbitals to make the covalent bonds. So now we're going to look at the hybrid orbitals and understand the hybrid theory and why this came for adaptation to explain bonding. Hybrid, like you know the word, it means mixing things, right? It's a mix of orbitals. So what we are trying to say that atoms do not use pure atomic orbitals, rather atoms use hybrid orbitals. And they are that process of mixing atomic orbitals is called hybridization. So we mix at least 2 non-equivalent atomic orbitals, meaning I mix s with p or s P and D, but it's not, you don't mix like S with S or P with P. That's what we mean. And with the hybrid orbitals have different shape from the atomic orbitals. And that does make sense, right? For example, pink is a hybrid of white and red. Pink is not white and it's not red. It's in between. The number of hybrid orbitals equal the number of the pure atomic orbitals that made them. Form bonds, the hybrid orbitals, they form bonds by overlap with other hybrid orbitals or atomic orbitals depending on the situation. So let's go back to ammonia. This is the nitrogen electron configuration. And what does happen there, remember, we are only going, and this is very important that I highlight from the beginning, we are only going to look at the valence, right? We don't really care about the 1s. Why? Only the valence is involved in bonding. At the valence, I have 1s orbital, and I also have 3p orbitals. So now I'm going to mix the 1s with the p orbitals. Let's look at the next picture. And again, nitrogen does have how many valence electrons? 5 valence electrons. So I am mixing now the 2s with 2p. They are together 1, 2, 3, 4. When I mix these together, I'm going to get 4 equivalent hybrid orbitals. Each one of them is called sp3. So this is an sp3 orbital. This is sp3 orbital. This is sp3 orbital. And this is sp3 orbital. They are equivalent. And the name, it's very simple. It comes from what you used to make them. What did I use to make each one of these? I mixed an S with 3 P's. So the name is sp3. Okay, they are equivalent. Now you have the total of 5 valence electrons. When you have 4 equivalent orbitals and you have 5 electrons to put on them, then the way we do it is 1, 2, 3, 4. Now I have to pair 5. So this is how they look. Now remember, I have 4 of them. Each one of them is called sp3. When you have 4 things and you want to separate them as far away from each other as possible, what is the best angle for that? And if you go back to our Vesper lecture, you will remember that the best angle for that will be the tetrahedral angle of 109.5. However, there is one orbital occupied by a lone pair, so that angle will be slightly less than 109.5, and it will be 107 as you have seen in the previous slide. So now hybridization does support the actual angle of ammonia and therefore can explain the bonding in ammonia. So now look at them. You mix these together, you mix the 4 orbitals together, 1s and 3p's, you're gonna get 4 equivalent sp3. They are purple on a purpose because they are neither blue nor red, right? They are a mix. And the shape of them does not look like S and it doesn't look like P's. It's somewhere in the middle, however, leaning more towards P because you used more P in the hybridization than you used S. And that separation will be 109.5. Now let's look at the next. This is now ammonia. Each one of these blue orbitals is an sp3 orbital. This here is sp3 orbital. This here, sp3 orbital, and this here is sp3 orbital, right? There are 4 orbitals. One of them has the lone pair. This one is making a covalent bond with an 1s of hydrogen, and another covalent bond with another 1s from the hydrogen, and another covalent bond with 1s of the hydrogen. So the hybridized orbitals are either hosting lone pair or pairs, depends, or they are making covalent bonds. All right, so again, this is predicted the correct angle in ammonia. Now, formation of covalent bond then can be explained, for example, for carbon the same way. Carbon used 4 hybridized orbitals, each one of them called sp3, with 4 hydrogens, each one of them is called sp. Now, there is another hybridization that goes on that we call sp2. An example is boron trifluoride. The VSEPR geometry of boron trifluoride suggested that we have trigonal planar. So, if we are to remember, boron is an exception. It is happy with 3 bonds or total of 6 electrons around it. And now when I'm looking at the covalent bonding here, I will immediately see that I have 3 covalent bonds. Each one of them is made from a hybridization on boron and the atomic orbital here on fluorine. However, boron only needs to make 3 bonds and it doesn't have lone pairs. So I only need 3 hybridized orbitals. And I only hybridize based on what I need, okay? So if I need 3 hybridized orbitals, all I have to do is to mix 1 s with 2 p's, because if I mix this, I'm gonna get 3 orbitals equivalent, each one of them called sp2, sp2, okay? So this is really what causes me to use an sp2 hybridization. It means I only need 3 hybridized orbitals. Now, when they are mixed, you're gonna get 3 hybridized orbitals. The best separation between 3 will be the 120 angle, and that leads to trigonal planar. Now, sometimes I might need the sp hybridized orbitals, and this is an example here where you have beryllium difluoride. The VSEPR geometry for that is linear. So, if you remember, this here will be the Lewis structure. It's an exception. It only needs 2 bonds around it, or a total of 4 electrons, which means beryllium needs 2 hybridized orbitals. How do I make 2 hybridized orbitals? I mix 1 s with 1 p. That's going to give me 2 identical sp hybridized orbitals. Since there are 2, the best separation between any 2 will be the 180 degree, leading to the linear geometry. Okay, so beryllium uses the purple orbitals, which are the sp orbitals, and fluorine uses its atomic orbital, which is the 2p orbital. All right, let's next. Now, sometimes we might need the hybridization of sp and d orbitals. And this can only happen with 3rd period elements, right? This is when I can expand my octet, and I can only expand my octet on the 3rd period elements and beyond, because they have the d orbitals. Here is an example. Sulfur hexafluoride. When you draw the sulfur hexafluoride, it's octahedral with 6 covalent bonds around sulfur. So sulfur needed 6 hybridized orbitals. How can I achieve that? So let's go back here. How can I achieve that? Let me show you. So this is sulfur. with 6 covalent bonds. It means sulfur needed to mix one S with 3 P's, and that's give you 4, and 2 D's. If it mixes all of them together, then I'm going to have 1, 2, 3, 4, 5, 6. Each one of those is called sp3d2. Exactly what it's made of. It's made of 1 S, 3 P's, and 2 D's. So now you might ask, how can I predict the hybridization of the central atom? It's always the central atom that we hybridize, guys, not the terminal ones. First, we draw the Lewis structure. Then we count number of electron groups for the central atoms. Just a reminder, how do I have the number of electron groups? It is number of atoms and lone pairs on the central atom. So let's go for it. If I have 2 groups, then the hybridization is sp, because I need 2 hybridized orbital, right? So I'm going to mix 1 S with 1 P. Example will be beryllium dichloride. The electron geometry in this case will be linear. If I have 3 electron groups, then it means I need 3 hybridized orbitals. How do I make 3 hybridized orbitals? I'll mix 1 S with 2 P's. That's going to give me 3 sp2. And that will give me an example like boron trifluoride, and the geometry will be trigonal planar. If I have 4 electronic groups, then the hybridization will be sp3. An example will be methane, ammonia, and water. And the electron geometry for this case will be tetrahedral. If I have 5 electronic groups, then the hybridization will be sp3d, because I'm mixing 1 S with 3 P's and 1 D to give me 5 hybridized orbitals. And that will be something like phosphorus pentachloride. And it will be, the electron geometry will be trigonal bipyramidal. If I have 6 electronic groups, then I have to mix 1 S with 3 P's and 2 D's to give me sp3d2, like sulfur hexafluoride, and that will be an electron geometry that is called octahedral. So now we understand how we got into the hybridization, how ammonia was behind that story, and how it always make us understand the bonding and the angles between the bonds. So here is another picture to explain that. We can look at the sp, where we have the purple orbitals are the hybridized orbitals. I have 2 sp hybridized orbitals with 180-degree separation. Then I have the 3 sp2 with the 120-degree giving you trigonal planar. I have the 4 sp3 with a separation of 109.5 degree. I have the sp3d with trigonal bipyramidal 120 degree and 90 degree, and I have the sp3d2 with octahedral, and the sp3d2 will give you the 6 sp3d2 hybridized orbitals, and the angles in this case, as you guys know, will be 90 degree. Now let's practice some hybridization together. Determine the electron geometry. What is the hybridization of the central underlined atom, and describe which of the orbitals overlap during the hybridization process. Let's look at that. Phosphorus trifluoride. I want you to pause the video and draw the Lewis structure of phosphorus trifluoride. Okay? If you do things correctly, then you have the following structure. Now, how do I decide hybridization? I count the electronic groups. How do I count electronic groups? Number of atoms and lone pairs around the central atom. I have 1, 2, 3 atoms and 1 lone pairs. I have 4 electronic groups. 4 electronic groups means I needed 4 hybridized orbitals, which means sp3 was the hybridization of the central atom. Now, for phosphorus, it will use sp3 to put the lone pair to make this covalent bond, to make this covalent bond, and this covalent bond. While fluorine will use its atomic orbital, which is the 2p, the 2p for fluorine, and the 2p from fluorine, right? Let's look at the next one. Phosphorus pentabromide. I want you to pause and take a moment to draw the Lewis structure of phosphorus pentabromide. And if you do things correctly, then this is the correct Lewis structure of phosphorus pentabromide. Now, phosphorus needed 5 electronic groups because it does have 5 atoms around the central atom. So what does that mean, hybridization? It needed 5 hybridized orbitals. How can I achieve that? If I mix one S with the 3 P's and 1 D. So the hybridization here will be sp3d, right? So phosphorus is using sp3d here, sp3d here, sp3d here, sp3d here, and sp3d here. And bromine will use its atomic orbital, which will be 4p for this bromine, 4p for this bromine, and so on for the rest of them. Beryllium dihydride, that's an easy one. This will be the exception. It only needs 2 bonds. 2 bonds mean 2 electronic groups because there are no lone pairs. It means the hybridization will be sp. I need 2 hybridized orbitals, so I mix one s with one p to give me 2 sp. So that will be an sp. So beryllium using sp here to make this bond, and sp here to make this bond. And for the hydrogen, it uses its 1s, and this hydrogen uses 1s. Now, hybridization in molecules with double and triple bonds. So the sp2 hybridization of a carbon, if you look, guys, at the picture that we are presenting here, we will look at the orbital diagram of the carbon atom. So you have 2 electrons in the s orbitals and 2 electrons in the p orbitals. However, there is a process that we call promotion that takes place. And in the promotion, one of the electrons in the 2s gets to be promoted to occupy the 2p. Then after that, the atom hybridize whatever it needs hybridization wise. All depends, of course, on the number of electronic groups, and that will leave 1 electron in a pure p orbital that was not hybridized. So in this case, this carbon specifically needed the 3 hybridized orbitals. So what did it do? It mixed 1s with 2 p's, because it only needs 3 hybridized orbitals. So that left this p orbital here to be kept pure, not hybridized, all by it all, having 1 electron in it. So that now gives me 3 hybridized orbitals, sp2, and 1 pure p orbital that was not hybridized, that I'm going to call it perpendicular on that plane. So this is an sp2, this is an sp2, and this is an sp2, while this here is pure p. This is a pure p orbital that did not get hybridized. Now remember, each one of them has an electron, including the pure p orbital. All right, let's move to the next slide. Here is an example of a carbon doing a double bond. If we are looking at the carbon, we're going to now identify the bonds as either sigma bonds, which are the orbitals overlapping end to end. Electron density is between the two atoms. And then we also going to look at something we call the pi bond. But first, let's look at the sigma. Sigma bonds are the ones, now remember, this carbon has sp2, sp2, and one of these is also sp2. Okay, so three covalent bond, we're going to call them sigma because those are made of the hybridized orbitals. Those are the purple ones. So this carbon has the sp2 here, the sp2 here, and the sp2 here. One is bonded to the carbon, which is this one right here, and two are bonded to the hydrogen. Okay, same thing applies to this carbon because also this carbon is sp2. And if you want to revise how I get this, if I am following the rules, what is the hybridization of this carbon? Count electronic groups. It has 1, 2, 3 atoms around it. So the hybridization is sp2. Now, this explains three bonds that we are going to call sigma bonds. It leaves this bond, I'm going to highlight this bond in, let's do the purple one here. This bond is still not explained. It's not made of the sp2 hybridized orbitals. What is it made of? It's going to be made of the overlap between the two pure p orbitals that are perpendicular to the plane. You see that blue plane there? This is perpendicular to the plane. And this is what we call a pi bond, right? Because remember, this has one electron and this has one electron. So when they overlap, they make a covalent bond because a covalent bond is made of an overlap of two electrons. So this is here showing the picture of what is a pi bond. Pi bond is when orbitals overlap sideways, electron density is above and below the plane of the nuclei, like the picture here shown in pink. So another nice representation here, look at it. I'm going to color code for you again. So the red ones are the sigma. Those are made of sp2, sp2, right? Same thing here, sp2, sp2, sp2. And then you have the purple one, which is the pi bond, which is made of pure p above and below the plane, which is that pink overlap right here. That is the pi bond. So because the electron density here is above the nuclei plane, while the electron density here is between the nuclei plane, that is a strong connection. Sigma is a stronger bond than pi. Keep that in mind. Now, what about sp hybridization? Again, the ground state of carbon, 2 electrons in the s orbital and 2 electrons in the p orbital. When we do a promotion, we're going to promote one of the s orbitals to go and occupy a p orbital. Then the atom will choose to hybridize what it needs. In this case, it only needs to hybridize one s with one p. So that's going to give me 2 sp hybridized orbitals and 2 pure p's, each one of them with an electron. So that now, if I'm going to make you see here, I'm going to explain the bonding step by step. Let's go first. This here is the sigma bond that's made of sp and sp. This is the other sp and this is the other sp that is used to make, and the molecule we are looking at is this one here, when carbon has a triple bond. This is here. So this is the sp hybridized orbitals and this is the sp hybridized orbitals, and one of those covalent bonds is also sp with sp, right? From one sp from one carbon and sp from the other carbon. Now, one I'm gonna make this one green. One is this p orbital that is perpendicular, and it makes this overlap right here, right? And that is 1 pi bond. The other p orbital, so if that was the pz, px will be sticking out towards you and going away from you on the plane, right? So in a different color here, let me show you. So this is not a clear color. Let's do this one. This is here the other p orbital that is perpendicular to the first one, and that will make an overlap in front and behind the sigma. So the green overlap is above and below the sigma, and the brown overlap is in front and behind the sigma. So I have 2 pi bonds. So this is a pi bond, and this is also a pi bond. 2 pi bonds and 1 sigma bond. Let's look at another picture for that. And now I can say that a single bond has 1 sigma. A double bond has a hybridization of sp2, and it is made of 1 sigma and 1 pi. A triple bond has the hybridization of sp, and it has 1 sigma and 2 pi bonds. So now let's look at this question together. How many sigma and pi bonds are in the acetic acid molecule? You have to draw the Lewis structure, so I'm going to do this here for you. This is acetic acid, Lewis structure. Now, every single bond is a sigma bond. So I'm going to color the sigma with red, okay? Sigma, 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 and sigma. Every double bond is made of 1 sigma and 1 pi. So this is 1 sigma right here, which means pi, I'm going to do in blue, this is 1 pi. So now count them. This molecule is made of 1, 2, 3, 4, 5, 6, and 7. 7 sigmas and 1 pi bond. Okay. What are the hybridization states of the carbon in the following molecule? The carbons are attached to each other in a chain. So let's draw this molecule together. It means there is a carbon that has 2 hydrogen, then double bond to a carbon that has 1 hydrogen, then it has a single bond to a carbon that has 1 hydrogen, and a double bond to a carbon that has 2 hydrogens. So now I'm going to teach you an easy way to figure out hybridization if I'm just asking hybridization. Hybridization, count your electronic groups. How do we count electronic groups? All the atoms and the lone pairs on the central atom. So let's look at that. So I have 1, 2, 3 atoms around this carbon. This means 3 electronic groups, sp2. Same thing here for this carbon. If I count 1, 2, 3 atoms, no lone pairs, 3 electronic groups, sp2. This carbon, 1, 2, 3, sp2. Let's look at this carbon, 1, 2, 3, also sp2 hybridization. That does conclude the hybridization lecture, and I will see you next in the molecular orbitals theory. Thank you very much.